Welcome to session number 3 of Simple Harmonic Motion. And what a day to conduct a session. It's 31st, the last day of one of the most special years. I'm pretty sure 2020 will go down in history for, different reasons, good or bad. So today we're going to talk about angular SHM, the pendulum swinging, and lot of oscillations coming up out here. So get ready to be hypnotized by me, your master teacher for physics at Vedantu going live. Hello everyone. So some of you are asking, what is your new year resolution? So my new year resolution is to just stay healthy, guys. Just stay fit and be happy. So remember, health is at the end of the day wealth. So my resolution is that. So what is your resolution? Why don't you type it out in the chat box and everybody else can also see it. Hello Shreya, Kirito, Fida and Yalni and everyone out here. So welcome to this session number 3. And in case you are new to this session, let me tell you a little bit about myself. So guys, I am Shreyas and I am the physics master teacher, not just for YouTube but also the regular sessions which are conducted on the Vedantu platform. So I teach a lot of batches and I have been teaching for quite some time now. And before joining Vedantu, I was in a lot of offline industries and where I was to coach, train students for cracking their JEE, Advanced, Mains, BitSat, CET, you name it. And many of my students have successfully cracked the examination and have secured even 2-digit ranks, all India ranks in the JEE Mains as well as Advanced examination. So having said that, I want to make sure that you enjoy physics, you learn physics and at the same time stay motivated, and that's what I want to do. I hope I'll be successful in my dream of reaching out to as many students as possible in this country, and this channel is dedicated for all the English medium students because there are hardly any English channels for JEE coaching in our country. So that's what our aim is right now. So good and glad that you are already here. So in case you want to know more about me and you want to follow my stories, you can follow me on Instagram. My Instagram handle is Shreyas_Vedantu. I keep posting a lot of updates out there. Hello Ajay, hello Asmi, hello Keshav. Welcome aboard everyone. Okay, so I'm seeing a lot of resolutions out here. Yes, slow mode has been enabled because of the spammers which had swarmed our chat box yesterday. So just for an experimental basis, I have turned on the slow mode just for today, guys, just so that we control things. Okay, so don't worry, it's just 20 seconds. So 20 seconds is not big, and I'm pretty sure you will be making notes. So that is also to quietly remind you, hey, you know what, you should also make notes. All right. Okay. So before going ahead, do not forget, guys, in case you are a new user, do not forget to hit the subscribe button. It's free of cost, obviously. And if you already subscribed, you should also like our video. Remember, unless you like my video, guys, I won't get that energy. So come on, go hit that like button. That's the fee. That's the payment you need to do for today's session. Go hit that like button. Hello, Akanshan. Hello, everyone. Okay. Chalo, let's begin then. And by the way, let me tell you that today at 5:50, yes, 6 o'clock, actually the minister is going to go live. So 10 minutes before, I'm going to give you all the important updates within 10 minutes. And it's going to be a short session. It's going to be a live session, live streaming session where the minister, education minister is going to give us the final dates and probably also the date sheet, the exact brochure. Hopefully the details will come out 6 o'clock. So stay tuned, guys, and come live at 6 o'clock as well. Do not forget that. And you can also pass on the message to all your loved ones and friends. And on Saturday next year, we'll be meeting for the marathon session. What an opening it would be, starting our new year with a marathon session on magnetism, magnetic properties, diamagnetic, paramagnetic materials, bar magnets, and so many other stuff. We'll be doing it on Saturday. Hello Gautam, welcome. Hello Sneha, welcome. So let's begin. And remember, on Sunday you are going to have chemistry Menti quiz, and maths Menti quiz was on Tuesday. In case you have missed it, you can watch it. So chemistry at 9 o'clock on Sunday. All right, so let's start. And we are going to start with the first concept called as torsion. Now, what is the meaning of torsion? Torsion means, twisting something like this. Twisting, look at this. So you twist something, that is called as torsion. And when you twist something, there is a restoring force. So when you twist something like this, there is a restoring force which brings it back to its original shape and size. Just like when you extend a spring, there is a deformation. That deformation is opposed by the elastic forces within that body. Same way, when you rotate a rod, there is a restoring torque, not force, torque, which will restore it back to its original shape and size. So that restoring torque will give rise to oscillations. Think about it. Imagine this is that rod, you deform it and leave it. It will try to restore itself, bring it back to its original shape and size. But by that time, it would have gained some momentum. And because of that momentum, it will go to the other side. And as soon as it goes to the other side, it will again experience restoring torque. So it will slow down, stop, and again it will try to come back. And it will again try to restore back. But again it will have some momentum. So again it will overshoot and go back to the other side. And this will continuously happen. And that's why it will be called as a torsional pendulum. I hope this idea is very clear now. Yes, so I hope this idea is clear. Though this is because of the elastic forces within a long, slender body. No problem, Kashyap. Join in, no problem. I just started. Okay, join in. All right, minions, come on, let's get going. So here is the concept, guys. In a torsional pendulum, so this torsion is nothing but for twist. So whenever a rod like object or a rod itself is twisted, okay, so basically I can say there is an elastic restoring torque, and this torque is proportional to how much you displace it, how much angular displacement is there. So this theta is the angular twist that happens, or angular displacement in radians. So this torque is in Newton meter. That constant is like K. You can call it kappa. It's almost like K. Okay, the English alphabet K. The Greek symbol looks like K. So this K is called as nothing but the torsional constant. So this is called as a torsional constant. I hope you can see the similarities between this K and that K of spring constant. In linear motion, force was Kx, correct? In linear motion, force was Kx. Here, the torque is K into angular displacement. That's it. But understand, if displacement is in one direction, the torque will be exactly in the opposite direction. So I'll put a minus sign if all of them are vectors, or if I'm following the sign convention. So if I twist it clockwise, the torque will be anti-clockwise. If I twist it anti-clockwise, the torque will be clockwise. So that minus sign just denotes that the torque is exactly opposite to the theta. So very, very similar. And the dimensions of this, you can easily guess. Torque has the dimension of Newton meter and theta has the dimension of radian. So it will be Newton meters per radian. What does it mean that, K is very large? If the rod's K is very, very large, then it means it's very difficult for it to twist. And if it is small, then it means it is very easy for you to twist the rod. I hope this is clear. So this is what you have in torsional pendulum. Okay, I hope everybody is understanding it. Hi Khushbu, hello everyone. Join in. So what material is a torsional pendulum made of? It can be made of any material. It could be plastic, it could be silver, it could be iron, doesn't matter. Everything will have some kind of elastic force which will try to restore it, Kirito. Okay, I hope that's clear. Hello Ayan, join in. Now, why are we talking about it so much? So you will see that if you take a rod or a wire which has some torsional constant, okay, which has some torsional constant K, and it is being suspended, and there is some body, it could be a disc, it could be a solid sphere, it could be a triangle, it could be a rod, it could be you, it could be Pandu, it doesn't matter. So you suspend something and you twist it, you will see it will come back, and it has momentum, so it will go there. Again there is torque, so again it will go back. Again there is momentum, so it will go there. So it will keep oscillating like this. It will keep oscillating like this. So that's what I want to do, guys. How to find what is the time period of oscillation. So let's figure out what's the time period of oscillation. I hope you guys are ready. So torsional strain is basically how much angular displacement you are having per unit length and all that. So we do not have all that, Fida, don't worry about it. Yes, so don't worry. Okay. Yes, it will break after a certain limit unless and until you have twisted it too much. So it will obviously break up beyond a limit. But we are assuming that we are not twisted it so much that it breaks. Then our problem only will not be there. So we are assuming that it is well within elastic limits. So now let me tell you a very, very interesting thing, guys. Very, very interesting thing. Observe this very carefully now. Okay. So on one side, okay, I'm going to write linear, oops. On one side I'm going to write linear motion, okay, and here you will have rotational or angular motion. Now you will see the similarities. See, the first thing that you saw is in linear motion the force of the spring is minus kx. In rotational motion or angular SHMs or oscillations, instead of force you have torque, and instead of k you have kappa, very, very similar, and instead of x you have theta. Okay, that's one thing. Now instead of mass, what will you have? You will have moment of inertia, guys. Think about it. Instead of mass you will have moment of inertia, correct? Now because it oscillates, correct, there will be a time period of oscillation, there will be omega and all that. So here the time period used to be 2 pi under root of mass by k, correct? 2 pi under root m by k. But here what can be the time period then? Think about it. The time period will be, instead of mass you will have I, and instead of k you will have kappa, the torsional constant k out there. I hope that's clear. I hope this is clear. Yes? Hello Ashutosh, join in. Okay, so I hope this is clear. Is that clear, everyone? Everyone understanding this? Okay. So guys, come on, ping your friends if they are not yet here. Come on, ping them somewhere on Messenger or whatever and ask them, come on, join in karke. All right. Now, next thing. Here we had x as a function of time, and that was a sine omega t plus phi, correct? This was the equation of SHM. So over here, you know what will be the equation? Instead of x, you will have angular position, correct? You will have angular position, and instead of a you will have theta max. Now what does theta max mean? See guys, if imagine I am a torsional pendulum, I go here plus 30, I go here minus 30. So I go like this, plus 30, minus 30. So plus 30 and minus 30 are my maximum angular displacements. So other times my angular displacement will be less than or equal to 30. Understand? So that's the maximum angular displacement. Understand that? Okay, great. So now if this is understood, so this will be theta max into sine of omega t plus phi. So that's the SHM's equation, position as a function of time. Remember, this omega which I am talking about over here is root of k by m in this situation for linear motion, but for angular SHM it will be root of kappa, or that Greek constant, torsional constant, by moment of inertia. That's the change. That's the change. Crazy, you can read my bio. By the way, I'm from NIT Nagpur. I'm a BTech from NIT Nagpur. Alright. So, if this is clear, then the next thing I want to tell you is every other equation what you have been talking about also has an equivalent equation in angular SHM, guys. Every equation, yes, you think about it, everything will be there. For example, velocity. What is velocity? It was a omega cos omega t plus phi, correct? This was the equation for velocity. Over here, the equivalent of velocity is angular velocity. Now, I will not use this symbol omega. Now, this is very important. Listen to me carefully. A lot of you are going to make mistakes. So, understand this omega symbol is now reserved for this omega, angular frequency. So do not use the same symbol for angular speed. This omega is angular frequency, radians per second. It tells you how frequently it is oscillating, and that is a constant. Why? Because kappa is a constant, I, which is the moment of inertia, is also constant. Understand? So omega is the angular frequency of the oscillation, which is constant. But speed, the angular speed will be different at different times. Sometimes it will be at rest, then it will be maximum, then zero, then maximum, then zero. So it will keep varying. So it's a variable. So instead of confusing you guys, we will use this symbol, guys, d theta by dt. D theta by dt, which is same as theta dot, the first derivative of theta. Because remember, even velocity was the first derivative of the position. So remember that. So we're going to use that as well. All right. I hope this is clear. So crazy, probably I can answer all your questions on Instagram, not over here. Let's focus on the session right now. Okay. So this will become, instead of a omega, what will you have? You will have theta max. You will have theta max omega, and instead of sine, you will have cos, and you will have omega t plus phi. All right. I hope this is clear. Okay, I hope this is clear. So that's the difference, guys. Be careful. This is not omega. I'm not going to use that symbol. It's already reserved for the angular frequency, which is a constant. This is not a constant. All other equations are also valid, like acceleration, etc. Whatever we have spoken about is still valid. But if you still want it, I will write it down. No problems. X double dot, which is acceleration, will be minus a omega, and you will have, this will be omega square, sorry, and this will be sine omega t plus phi. That was acceleration. But here you will have theta double dot, which is angular acceleration. That symbol luckily does not match with anything, so I can use that alpha, and that will be minus a. Instead of a, you will have theta max, and instead of omega, you will have omega square out here, and instead of cos, you're going to have sine omega t plus phi. So you can see the resemblance in all the equations. It's very, very identical. It's very, very identical. Hello Naomi, hello Bhargav, very good. All right, crazy. Okay, so hello everyone, join in. Even if you are late, just join in. So you can see a lot of resemblance. So if you know linear SHM, and if you have been attentive during my classes of linear SHM, obviously it's going to be very simple out here when you study rotational or angular SHM. All right, so let's get going. And now I hope you have taken a screenshot, or you have also made notes. Okay, let's get going then. Okay, now hold on. Okay, so like you can see, this body which is attached over here, theta m is the maximum angular displacement. The time period of this pendulum, will be 2 pi under root. Instead of m, it will be moment of inertia, and instead of k, it will be kappa. So this k is the torsional constant of this wire, and this I is the moment of inertia of this body which is suspended over here. And you can use everything else. Frequency is 1 by time period, and omega is 2 pi f, or which is also 2 pi by t. Everything, whatever you have learned in linear SHM can be used over here. Understand that. So theta m is also referred to as angular amplitude. This is called as angular amplitude because this is angle wise. So this is angular amplitude, remember that. Okay, so I hope everyone is understanding all these pointers and these notations and whatever definitions I have given out here. Also this 0 over here, this reference line, also stands for the mean position, guys. So this is the mean position of that particular body. And these two out here, this one and this one, both of them, these both are the extreme positions of that oscillation. Okay, fine everyone. Okay, Kashyap, torque is the equivalent of force, okay, in a rotation. So I am not sure which grade are you in. If you are in 10th standard, most likely you will be asking this doubt. So think of torque as the equivalent of force in rotation. So only a torque can cause a rotation. Okay? So you can also attend my classes in the playlist. I have made a beautiful playlist explaining all the concepts of rotation, and one such session is also on torque. Alright? Alright, yes sir, you are also from Bangalore. Very good. High five. Very good, Anam. Very good, very good, very good, Fida. Nice gesture from you for explaining all the stuff. Very good. You minions are doing great. All right. So let's solve the first question. Come on, guys. Let's see how many of you get this. Come on. Let's see how many of you get this. The motion of a torsional pendulum is question mark. And what do you say, guys? Is the slow mode good? Should the time limit be 20 seconds? Or should it be more? Or should it be less? What do you guys say? Alright, Akansha says B. Sneha says B. Krito says B. Alright. Anam, I'm not exactly the bro, but I'm your master teacher. So you can just call me Shreyas Sir. But I've been reading your comments. Thank you for all the love and support. Alright. Welcome, Gree. Glad some of you have recommended Gree. Very good. Welcome, Gree. Join in. All right. Okay. So, by the way, more than one are correct. Hint: more than one are correct. More than one are correct. Come on. More than one are correct, guys. Think about it. The motion of a torsional pendulum is more than one are correct. Come on. Acha. All of the above. Acha. Little bit confused. Okay, I'll show you the answer. The correct answer is A, B and D. It's not simple harmonic, it is angular simple harmonic. Simple harmonic linear motion will be like this. Torsional motion is like this. So this is angular simple harmonic motion, and periodic, obviously oscillatory, yes, because it is oscillating and it is repeating itself, so it has to be periodic, and it is angular SHM. Alright, crazy, I can't answer yeah, because understand, the session is going, the flow is going. I can only answer after the session. So if you can post all your doubts in the comment section after the video is over, definitely I'll answer, or you can ping me on Instagram. I'll answer all your doubts out there. Alright, okay. So next question, here it is. Let's see how many of you can get this. There is a disc which is attached to a rod. The disc has a radius of 10 centimeters, mass 200 grams, fixed to the center of a metallic wire. The other end is hinged, it's not allowed to move, with a clamp. If the time period of the disc's oscillation is 0.2 seconds, what is the torsional constant of that wire? Come on, you can figure this out. Alright, figure this out. Come on. Shreya, the thing is, just simple harmonic, linear simple harmonic means, it's going along a straight line. So angular SHM means theta is a function of sine or cosine. So when x is a function, so it's just linear simple harmonic, alright, and otherwise it will be angular SHM, okay. No crazy or not interrupting, don't worry, but just get in, blend in, with others, and try to follow whatever I'm teaching, and you'll enjoy it more, okay. So don't worry, there will be special sessions just where I talk about myself and other stuff, okay. Akansha, I guess you joined little bit late, but you missed the basic stuff, but don't worry, I hope you'll catch up later on, and after this you will see a completely different topic, don't worry. Alright, okay. Chalo, let's see how to solve this question. Now use the formulas given, guys. First of all, radius is 10 centimeters means 0.1 meter, mass is 200 grams means it is 0.2 kg, and time period is also given. Now time period formula is 2 pi under root. Instead of mass you have moment of inertia, and instead of k you have torsional constant, equivalent of spring constant in rotation. That's all you need to think about. Now before we solve anything further, think about it this way. I can write it as, okay, I can square both sides. So it will become t square is equal to 4 pi square, correct? And here you will have I by k. Now take k over here and bring this t square down. So this t square is down and this k is on the top. So I just rearranged it. Now what I'm going to do is 4 pi square. I'm going to write down the formula for moment of inertia, and that is mr square by 2, and the time period square will be as it is. So I just need to start substituting all the values to find out the value of k, guys. That's about it. So 4 by 2, so that will become 2. So it will become 2. Pi square is approximately 10. Approximately, guys. Everybody knows this approximation. Mass, that's given. How much is it? 0.2. And r square. R is 0.1. So 0.1 square divided by time period square. So it will be 0.2 whole square. Now just do this and let me know what the answer is. Yes, it should be 1. Almost. Bhargav, Kirito, I think you over-calculated. I think you forgot the powers of 10. Yali, just check it once more. Just check it once more. All right. Yes. So just check if it is approximately 1. Approximately 1 Newton meter per radian. That is the answer, guys. Newton meter per radian. Yes, Fida. Yes. Very good. Very good, Esther. Very good. Yalini. Very good. Akansha. Excelente. Excelente. Let's get going. I hope you guys are now confident about torsional pendulum. Remember one thing. I gave you one chart. Remember that chart where I have like very nicely, beautifully classified on one side linear SHM and on the other side angular SHM. If you know the formulas for linear SHM, you already know the formulas for angular SHM. Just that the variables will change. Instead of mass, it's moment of inertia. Instead of spring constant, it's torsional constant. Instead of, let's say, x, it's theta, and so on and so forth. Oh, no problem, Kirito, no problem. Okay, chalo, let's get going. Now to the next thing. Okay, it's approximately 1. So if you put the exact value of pi, this is what you get, 0.986. It's okay. Very close. Now let's talk about something called as the physical pendulum. Now, you know the best part about today's lecture? I am going in the exact opposite way of what most of the institutes do. They start with simple pendulum, then physical pendulum, then torsional pendulum. But over the years, my past experience says that the exact opposite way is much better to understand this angular SHM. So that's what we're going to do. Oh well, Kashyap, unfortunately 2 o'clock, I'm not sure whether I can see it every day. I'm not sure, guys, if I can do it. All right, studies, yes, your chat is visible. Okay, so now let's talk about what is exactly physical pendulum. Guys, remember those days when you used to go to school back then in 2019? Yes, and you used to sit on the bench and your legs used to shake. All right, the legs used to shake when you're getting bored, you're just whiling away time, and then maybe somebody scolded you, hey, don't do that, you know. So guys, it's exactly that. So physical pendulum is any object suspended from a point and you disturb it, it oscillates. You disturb it, okay, so you disturb it, it oscillates. That is basically called as physical pendulum. That's it. That's it. That's called as physical pendulum, guys. And now you will be like, sir, then what is simple pendulum? Hold on, let's do the complicated or the complex pendulum first, and then let's go to simple pendulum. So this frog is definitely a physical pendulum, kind of. Okay, so understand, if I take any body, that body will always possess center of mass. Let's say this object over here has its center of mass somewhere over here. All right, this object's center of mass is here. Now if I exactly hold over here at the center of mass and I displace it, okay, if I exactly hold it at the center of mass and displace it, what do you think will happen? If I rotate it, it will just stay there. If I rotate it here, it will just stay there. If I rotate it like this, it will just stay there. Why? Because there is no torque. Why is there no torque? Because mg is passing through the center of mass and you are holding the center of mass, so there is no separation, so there is no torque. Understand? I hope this is clear. So there is no torque when you hold the object at center of mass. That's the problem. Only when there is some separation, then you will see the oscillation is there, and that's what is going to happen out here. This is some random object, guys. Some random. Doesn't matter what it is. What is point O? All right. Let's see what is point O. So guys, point O is nothing but the point of suspension or the hinge point. Okay, that's what it is. What is this L? This L is the distance from the point of suspension to the center of mass. So I'll write it over here. Distance from the hinge to the center of mass. Exactly. Now, if you draw the free body diagram, things will be very clear in your mind. This mg is going to pass straight down, okay, and what has happened is this body usually would have stayed like this. This center of mass would love to be here, isn't it? Center of mass will always try to be as low as possible. That's what every object's tendency is. Now you have moved that body. It doesn't like it like that because the center of mass is saying, hey, I want to be down there. I want to lower my potential energy. Bring me back, put me down, leave me. Okay, so that's what it's screaming and telling us. So this mg is down and this mg will have two components. Guys, think about it. If this is theta, this will be mg cos theta and this will be mg sin theta. I hope you can see that. That's mg cos and this is mg sin theta. Now, if I ask you, who is going to provide the restoring torque? Who is that restoring torque out here? Is it mg cos or is it mg sin? Is it mg cos or is it mg sin? Yes, a COM wants to be happy. Correcto. So, is it mg cos which is going to provide torque about the hinge or is it mg sin theta? Think about it. Yes, very good. Excellent, Mr. Rara. Very good, very good. Akasha, think about it. It's mg sin. Yes, Kirito. Very good. So, it's mg sin theta and the distance is L. So, the distance is L and the force is nothing but mg sin theta. So, remember torque was Rf perpendicular. This is F perpendicular to that line. So, F perpendicular R, that is torque. And some people like to put that minus sign just to tell, ki, hey, you know what, that is restoring in nature. Okay, but I know that it is restoring because it is trying to bring it back. So, I'm not putting that minus sign, but if you want, you can put it. No harm in that. Okay, so that minus just denotes, okay, so this minus sign just denotes or emphasizes on this word restoring. That's all. Okay, that's it. Now here is the catch. Is this SHM? The answer is no. You might be like, sir, come on, we have done it. Torque is proportional to sin theta, so it should be SHM. Exactly my point. Torque is proportional to sin theta, not theta. Only when torque is proportional to theta, only when force is proportional to x, only then it performs SHM. So here torque is proportional to sin theta, not theta. So what do? We'll make it theta. We'll be like, what the hell? How did you do that? How are you permitted to do that? I am permitted to do that. How, sir? How? Exactly. So the thing is, I know these questions might be running in your mind. How the hell did you make sin theta into theta? Guys, there is a simple mathematical approximation. Simple mathematical approximation. And what is that? Sin theta is approximately theta when theta is small. That's it. How small? Typically less than 30 degrees. Don't believe me? Do one thing. Use your calculator, convert it into radian mode, find sine of 0.1 radian, find sine of 0.075 radian, find sine of 0.089 radian, etc. You will see sine value will come out to be same as the inside angle when theta is small. Obviously sine of 2 radian won't come out as 2. That's stupidity. Okay, so that's not going to happen only when theta is very small. Oh, that means this performs SHM only when theta is small. So basically it is an angular SHM only when theta is small. Very, very important. Now guys, think about it. This thing over here, LMG. What is this LMG? That's equivalent of K, because torque is something into theta, right? Okay, I have to put that minus sign. I'll just put that minus sign as well. So torque is proportional to theta. What is this? This is a constant of proportionality. So guys, think about it. If I ask you now, what is the time period? What will be the answer? 2 pi under root I by K. What is K? This guy. LMG. That is the answer. So this is the time periods formula for a physical pendulum. Believe me, this is the formula. Hello Shreyas, join in. Understood guys? Okay, I hope this is clear. Yes. So we can take theta equal to sine. Yes, 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 you can do that. Excellent. Shall we start solving some problems now? Let's get ready. Come on, remember this formula. Time period is 2 pi under root I by LMG. What is L? L is the distance from hinge to center of mass. Remember that, okay? And I is moment of inertia of whom? The body. About which axis? About the hinge axis. Not about center of mass. Be careful about the hinge axis. Okay, be careful. Let's start solving a problem. Here is the first question. It's nothing but a rod like this. It's a rod like this. Harsha, that's equivalent, remember? Force is kx. Similarly, torque is something into theta. So that something is equivalent of k. I hope that makes sense. I hope you were also there at the start of my class. Okay, so that's how it is k. Okay, I hope I have explained it. So imagine there is a rod, I displace it and leave it. It's going to oscillate like this. I want to find the time period of oscillation. Guys, if you're already here and if you're new, you know what to do. You should hit the subscribe button. Come on, go hit the subscribe button down there if you have not done it yet. And if you're already subscribed, you know what to do. Hit the like button. Come on, go hit the like button for me. Show some love, guys. Come on, come on, come on, do that. Okay, so here is the thing. How do I find out the time period when this rod is going to oscillate back and forth like this? So use our formula. It's a physical pendulum. Okay, so what is the formula for physical pendulum? 2 pi under root m instead of mi, and instead of k it will be mgl. Okay, so now 2 pi under root. What is the moment of inertia of a rod about its end? Remember, the rod about its end has a formula ICM plus ml by 2 whole square, and this ICM was ml square by 12. Correct? Now be careful, this L over here is the distance from center of mass to hinge. Okay, be careful, little bit. Okay, first let's get rid of this first. What is the moment of inertia of that rod about its end? It will be ml square by 3. You should know this by parallel axis theorem. I've shifted the axis from center of mass to the end. You would have done this in rotational mechanics or rigid body mechanics. We have done this, guys. Come on. And so the moment of inertia comes out to be m total length of the rod square by 3. Now just start substituting. It will become m l square by 3. The whole thing divided by mg. Be careful. This L is not L. It is L by 2. This is distance from center of mass to hinge. It's exactly midway, so it should be L by 2, guys. So that's the catch a lot of people forget. Correct? Yes, very good, very good. So this answer should be 2 pi under root mm gone, one of the L's goes, it will become 2L by 3G, and most of you have written it down. Excellent, guys. Very good, minions. Very good, very good, very good. Excellent. Excellent, excellent, excellent. Great. Chalo, now I'll show you a beautiful problem. I'll show you a proper advanced type of question. Okay. Now look at this. Let's look at this. Okay. Done. Now look at this problem. There is a, yes, I know you. Some of you forgot that L. There is a ring. Okay, I've just stolen a bangle, guys. Okay. Shh, secret. Okay. So find the time period of this ring-like object when it is suspended through a point on its periphery. All right. Now, imagine this ring is over here. I hope everybody can see this. Okay. And guys, what I'm going to do is just displace this ring like this. You will see that it oscillates. Correct? So it goes like this and it goes like this. So this ring, when it is held here, and this is the axis, this pen is the axis, it goes like this and like this. I hope everybody is able to visualize this. All right. So this is how the ring is oscillating back and forth. So Now I want to figure out what is the time period of this ring's oscillation. Okay, come on, think about it. This time period will be 2 pi under root I. So what is I? Moment of inertia of the ring about the top point. Be careful. This was the axis. I'm shifting it. So shift it, guys, and then only write the formula. It will be mr square. That's the formula for the ring's moment of inertia about the central axis shifted by r. So mr square. I hope this is clear. Mr square plus mr square. Be careful, for a disk it is mr square by 2, for a ring it is just mr square. So mr square plus mr square, parallel axis theorem. So I have used parallel axis theorem, guys, over here. So to shift it, I have shifted it by r, do not forget it. Next, divided by mg, distance of center of mass from the hinge point. How much is it? It's r, guys. So it will be mgr. So it will become nothing but 2 pi under root mr square plus mr square, 2 mr square, gone, rr gone, 1r remaining. So 2r by g. That should be the correct answer. Just check it out. I hope this is clear. Is it clear? Is it clear? Is it clear? Is it clear? Now I'll tell you what is the trick in this. What can be another question which can make it very tricky actually. Okay, now I'll tell you what is the interesting part in this problem. Alright, so here it is. Guys, this ring may not just oscillate in this plane. This plane, yes, it can oscillate like this, but it may not just oscillate in this plane. It can also, just because you have suspended it here, it can oscillate like this. Visualize it. It can oscillate like this. I hope you are now able to visualize that the axis is here and the ring is coming forward and backward. So if you look at it from the side, it is going like that. Earlier, the ring's axis was here and it was oscillating here. Okay. Now I'm saying the axis is like this and the ring is oscillating like this. So that's a completely different oscillation. And now I'm interested, what is the time period for that kind of oscillation? So let's think about it. Let's think about it. Let's redraw it. Now my axis is like this, and it's a little bit difficult, I know, for most of you to visualize. So here is my thing, guys. I want to find the moment of inertia about this axis, right? So I need to know the moment of inertia about this diameter. If I know the moment of inertia about the diameter, I can shift it by r, only then I can find it out. Only then I can find it out. So first, what will be to find this I, think about what will be the moment of inertia about the diametrical axis. Now to do that, I have to use perpendicular axis theorem. Yes, I have to use perpendicular axis theorem. And if I call this as I1 and this will be also I1, think about it. I1 plus, I'll do it here maybe, I1 plus I1 will be moment of inertia about this axis which is coming towards you. Think about it. I1 is here, I1 is also here. Why both of them are same? Because if you rotate it like this or like this, it's the same thing, it's the diameter. Like this or like this, it's the same thing. Now, since both of them are perpendicular and this is a planar object, what will be the moment of inertia about this axis? Use perpendicular axis theorem. Correcto. So this will become mr square, guys. This is something which we know. Moment of inertia about this axis. Coming like that. I know that. So what will be I1? I1 will be mr square by 2. But I don't want I1. I want this I. So what will that I be? It will be I1 plus parallel axis theorem. Mr square. And how much will that be, guys? Mr square by 2 plus mr square. 3 by 2 mr square. 3 by 2 mr square. So what will be the time period? 2 pi under root moment of inertia. 3 by 2 mr square by mg, distance of center from hinge is also r. So it will become 2 pi under root of gone, rr gone, 1r remaining. So 3r by 2g. It's completely different from this answer. Completely different. So you need to pay attention to the wordings of the problem. You need to make sure that you have understood the question correctly, because the examiner could mean this and you might interpret this or the other way around. So read it carefully. What a brilliant question. Yes, definitely, Esther. And if this kind of question would be asked, remember that would be the most challenging question for that NEET examination, which very few people will do, and that will decide whether you will be a topper or not a topper. Because average questions everybody will be able to do, but the special questions, they will keep 1 or 2 difficult questions. Alright? So that's what will happen. Okay, great. Chalo, let's get going to the next question. Hi Ganesh Babu, yes, 1D, 1F. I'm not sure. Is green color not so much visible? Is it, guys? Is it? Is green color not so much visible? Okay. Green is epic. All right. Kiruto has his own words. Epic. Okay. All right. Cool. Let's get going. Then I'll try to use less of green. No problems. But I have very few colors left. There's one black. There is one red, and there's that blue which is hardly having any contrast. So green is the only option left. Okay, fine. So, by the way, guys, if you are interested in learning under me and Shimon Sir and other teachers and whatever, we are conducting a lot of micro courses in different batches. So, if you want, like say for example, the derivations of all the chapters or the discussion of H.C. Verma booklet and stuff like that. So, there are a lot of micro courses which we are running. And otherwise also other teachers are also running many micro courses, and they are conducting crash courses, regular batches, long-term batches, and you are still not late. Let me tell you one special thing about Vedantu. So guys, no matter which time of the year you join, there is always a batch waiting for you which will start at that point of time. Every month there is a batch, right from April right till November, December, January. So guys, you are never late, because some people realize it's late, or for some XYZ reasons they shift the institute or something like that. So there is always a batch ready for you. So go ahead, check it out, all the details, because you get doubt solving, test series, assignment, board preparation, KVPY preparation, micro courses, and you also get live doubts along with after the class doubts, and lots of long-term batches which you can choose from. So look at the prices. The prices are also mentioned. In fact, if you open the link, you can check it out later on. So prices for the 12th batch, then this is for the 11th batch, and this is for the dropper batch. Just go check it out, because you get 20% off just because you're going to use the coupon code SHHPRO. 20% flat off on that. So use that discount coupon code. The link for all the courses is in the description box below. Please go ahead and check it out. All right. Okay. Now let's talk about simple pendulum. Okay. So green is little bit less visible, is it? Okay. Okay. I'll use little bit less of green. Acha. Now what is simple pendulum? Simple pendulum is only different by a small thing as compared to a physical pendulum. Hi Kesavan Raja, welcome, join in. Get ready to get hypnotized. Okay, so the only difference is, in a physical pendulum, you had a big body suspended at a point. In simple pendulum, it's not a big body, it's a point mass. Everything else is massless or negligible mass. That's the only difference, nothing else. That's the only difference. So point mass suspended by a thread or a rod which is having very less mass as compared to the point mass, that is nothing but a simple pendulum. So now I hope you understand, a simple pendulum, is it not a special case of physical pendulum, guys? Is it not a special case of physical pendulum? What do you guys say? Yes, it is. Okay, so Fida did not get hypnotized. I'm not sure whether others got hypnotized and they are in some dream world now. Okay, so by the way, have you ever got hypnotized, guys, by someone? What do you believe? Like, is it possible to hypnotize someone? What do you guys say? Have you faced any incident like that? At least I have, but I did not get hypnotized. Oh, Kashyap says he has. Nobody else has. Hacha. Hi Vignesh, join in. Nobody. Okay. I don't know, but I remember once when I was in 9th or 10th standard, I had attended one function in my, I don't know, 10th standard some coaching I had joined, test series ke liye and all that. So that time there was some function and there was some guy who came and he claimed that he could hypnotize people and he called in some volunteers. Obviously I didn't go. I was like, no, I don't want to get hypnotized. I just hid my face and sat down in the audience. Some of my friends went and they were on the stage, and what happened after that I'll tell you after some time. Okay, just hold on, let me just complete simple pendulum. Okay, so here it is. Simple pendulum, the difference, like I was saying, is that the entire body's mass is concentrated here, that's thing, and this length does not have any mass in it. So just like before, mg is going to act down, mg sine theta, where theta is the angular displacement from its equilibrium position. This is where it wants to be, this is where it doesn't want to be. So it has been disturbed, obviously, so it tries to come back because of this restoring force. So now what is the time period of a simple pendulum? Very simple. Okay, so 2 pi under root moment of inertia by mg, distance of center of mass from the hinge is exactly the length of the rod or the thread, so it will be L only. But what will be the moment of inertia? Moment of inertia, think about it, will be point mass distance r mr square, that's it. So it will be just ml square, guys, just ml square. Are you able to understand? Just a point mass distance r, so ml square, that's it. So mm goes, ll goes, so it will become 2 pi and the root L by G. So special case, guys, very, very important, so you should know this. 2 pi under root L by G. Now there is a special case, and that is called as seconds pendulum. Seconds pendulum. So what is this seconds pendulum? So in seconds pendulum, the time period is not 1 second. The time period is, it takes 1 second for the tick and 1 more second for the tock. So tick tock is 2 seconds. Yes, that's how it became 2 pi under root L by G. Yes, so seconds pendulum has a time period of 2 seconds. And now if you substitute the value of time as 2, it will become 2 pi root of L, I don't know, G, I can write it as pi square. Guys, think about the approximation what I'm doing. Isn't G pi square approximately? Use that. Why? Because pi will be by. Right? This is under the root. So pi by 2 gone. So I'll have 1 is equal to root of L. Therefore L, this is all approximate because approximately I have wrote G as pi square. So length will be approximately 1 meter. So the length of a seconds pendulum is approximately 1 meter, guys. Oh yes, I know, Firda, TikTok is banned, but at least not banned on the board. Cool. Yes, you can try it out. You can take a thread, you can take a marble, you can take a point mass and see if the time period is approximately 2 seconds for a length of 1 meter. Very interesting stuff. So let's get going to some questions. Come on. Here's the first question coming up on your screen. A seconds pendulum is arranged in a lift. If the lift is moving up with an acceleration of g by 4, its new time period will be how much? Oh, I don't think the old time period is given. Oh no, it's given. It's a seconds pendulum. Yes, it's a seconds pendulum. Okay, come on. Think about it and let me know what should be the correct answer. A seconds pendulum is taken in a lift which is accelerating up with g by 4. Come on, think about it. What should be the new time period? Come on, guys. Come on. Think what will change. Hint, G will change. So because of that, time period will change. Think about it. Come on, guys. Thank you, Frederick. Same to you and all your family members. And by the way, I'll be saying Happy New Year to all of you at 6 o'clock today, 5:50, 6 o'clock. All right. So do not forget to attend that session. Very important session for all the 12th and dropper students especially. So I'll be wishing all of you happy new year there as well. Okay, so let's see the correct answer. What you should do is nothing but, see guys, time period is 2 pi root of L by G. Now length is the same, so that means old time period by new time period. So T1 or rather T2 by T1 will be root of G1 by G2. That's how it works. Now the new time period T2 is something which I don't know. T1 is nothing but 2 seconds because it's a seconds pendulum. Time period is 2 seconds. This is equal to root of G1. G1 is the old G when it was in a stationary lift. So that time it would be G only. But second time when it is in a lift which is accelerating up, it's accelerating up with G by 4. Think about it. If lift goes up, everything will fall down. So the G will increase. So if you are in a lift which accelerates with G by 4, this thing here relative to the lift will fall with G plus G by 4. That's the relative acceleration. G plus G by 4, it's falling faster. So substitute the relative G, G plus G by 4 guys. So now G gone. So you will have T2 by 2 is equal to root of 1 plus 1 by 4, 5 by 4. 4 goes on the top, so it will become 4 by 5 like this, and move it around. So it will become T2 is equal to root 4 is 2, 2 2s are 4. So it will become 4 by root of 5. That should be the answer. Yes, I hope this is clear. So let's just check whether it is correct. Yes, 4 by root 5 seconds. That's the answer guys. Correcto. Alrighty, alrighty. So SL, which part you did not get, please let me know. Alright, I'll help you out. Okay. Very good, very good. Come on, last 1 or 2 questions and we are done. I'm going to show you the homework and also the Ekalavya batch as well. I'll tell you about that in case you are new out here. Okay, anything which is not clear? SL, come on, tell me, quickly. Waiting. So, if anything is not clear about this. Okay, lift G, acha, that part. Okay, see, I'll tell you what. If the lift is at rest, if you drop something, what acceleration will it fall down with? G only, correct? It's just a stationary lift, it will fall down with G. But if the lift goes up with A, then understand this ball is not only going to fall with G, but because the lift is moving closer by A acceleration, so it will be G plus A. So that will be the perceived gravity inside the lift. So for everything that is inside the lift, you will use G plus A instead of G. That's it. And if the lift is going down, then everything will have, because understand, the ball will be falling with G, actual G, and the lift is coming down with A. So for the lift, the relative acceleration will be G minus A. So for the lift, it will be G minus A. That's the difference. I hope this is clear. Okay, so that's how it works. Okay, great. I hope SL, that's clear now. Chalo, let's see how many of you can get this. A child swinging on a swing is standing in standing position. A child is swinging on a swing in standing position and she suddenly sits on the swing. Then the time period of the swing will increase, decrease, remain same, can't say. Excellent SL. Come on guys, if you're already here and if you have not yet liked the video, go ahead and like the video, and if you're a new user, go hit the subscribe button, it's for free. Come on, go hit the like button if you're not done it yet. Alright, Sneha says B, Krito says A. And you can try it out next time you visit a park, what exactly happens to the time period. It will be fun to watch. Actually, you can do it practically as well. So, come on, waiting for a few more answers and then I'll show you the correct answer guys. Alrighty. Chalo, let's see the correct answer then. In 3, 2, 1, go. Okay, the correct answer is increases. Now I'll be like, why the hell does it increase? So, guys, think about it. When the champa, okay, is on that swing. Okay, I hope that swing is fine, whatever. Okay, and she's swinging like this, the jumper, and she's standing. Okay, now if she sits, okay, so think about this position when Champa is sitting. Oops, I don't know how to draw it. Okay, so this is sitting Champa and this is standing Champa. Alright, I hope I have drawn it very clearly, and I hope you give me 100 marks for the drawing as well. Okay, so think about it. When she's standing, the center of mass is closer to the hinge. When she's sitting, it's more away. So here it is closer to the hinge. Here it is away. Now think about it. When the center of mass goes away, think about pendulum, guys. 2 pi under root L by G. 2 pi under root L by G. L, if it increases, time period also increases. So hence the answer is increases. Okay, I hope this is clear. Glad you're back, Shushbu. What happened? I guess your internet went off. Okay, so that's the correct answer. Cool. So let's get going. Increases. So first of all, congratulations Ankit and Yalni for posting the answers for yesterday's homework. So in case you have not done it yet, please complete it, because I'll be posting the solutions. I would advise to do those homework questions before checking out those solutions. Very good. And I'll be posting whosoever will do these questions as homework, their names will pop out in the next session, guys. Not today, but after we come back. So a simple pendulum of length L1 has, this is not HSA, has a time period of T1, and another pendulum has time period T2. What is the time period of a pendulum of length L1 plus L2? That's your first question. And second question is, the mass and the radius of a planet are doubled. Then the time period of a simple pendulum, if was T, then what is the new time period? So that's what is the question. Come on. All right. So do these two questions. And guys, remember, Ekalavya test is on 3rd of January. And those of you who do not know about Ekalavya, remember, this is a special batch for NEET as well as JEE. Yes, there will be batches where you will be prepared for the JEE advanced examination with teachers like us. Last year, I, Shiva Sir and many other teachers have been teaching in Ekalavya batch. And you will have special sessions by AP Sir, Pulkit Sir as well. And there will be test series for all the mains as well as advanced. In fact, there are 900 special questions, special assignment called surgical strike with 2000 questions and 5-part, and full syllabus there will be 15 plus. And all this will also come with post-advanced mentoring. So for college counseling, decision making, what should you do, which branch should you take, we'll have counseling session as well. And these are the ranks which we produced last year. All India rank 41, All India rank 43, and there were more than 550 people who got selected in advanced just from the Vedantu's Ekalavya batch. So that's how it is. So Esther, you'll be getting all this homework in the session PDF. Check out the description link as well as the Telegram group. You'll get the PDF of the session, and you can download that PDF and you can check the end of the PDF. You can use that. All right. So yes. So you can also see the rank improvements, guys. The mains rank was 72, advanced rank after joining Ekalavya 635, and similarly for others. So you can see the delta, the change that we have produced in all these kids, and that's what we intend to do. All the things are very open. We are a very transparent organization. Every detail is put up on the website as well as the session PDF, and we also mention all the names properly, everything. So go check it out. All right. And in case you are not in 12th standard or a dropper student, so please spread the word, guys, because this batch is for free, zero cost. No hidden charges, nothing at all. This is completely free. We are not going to midway say, hey, for the test series you need to pay. Hey, you know what? We are going to launch one more thing extra and you have to pay for that. Nothing at all. Till the end, including the counseling. The only thing is show your love, respect, support. That's it. Nothing else we need from you. Okay. And this is a form link which is also there in the PDF. So these are the test dates. These are the only entry points for getting inside the Ekalavya batch. There is no other way to get inside the Ekalavya batch. So you have to fill the form and give these tests. So also other details will be shared on the Telegram group of Enthuse. Go check it out. So 1D1DF, I just said 550 plus people got selected for JEE Advanced, not mains, advanced. That is more than, so mains will be more than that. Yes, Khushbu, even for NEET students it will be there. Yes, Khushbu, last year we started off with NEET batch also, and lot of NEET students also cleared it. And I think Anand sir will be making a special announcement for NEET as well as JEE students on 2nd Jan. You would have already checked the video which was posted on our channel by Anand sir, our very own co-founder, guys. So please check it out. So he is going to make a special announcement as well on 2nd of January. So don't worry NEET students, don't worry JEE students, we are all there for you. We are not going to differentiate. You guys are all our kids. So we're going to show all the love and support for all of you. Don't worry. Okay. So guys, if you all love today's session, you know what to do. Go hit the subscribe button and go hit the like button. All right. So go hit the like button if you're already subscribed. And come on guys, spread the joy, spread the love. You guys should be sharing this channel link. You should get your friends also along. Tell them you're having an amazing time, and you will also have an amazing time when your friends are here. So guys, come on, call your friends as well. Chalo, bye bye, take care. See you again at 5:58 p.m. sharp today, the last session of the year with me, Shreyas, your master teacher and anchor for this channel. Bye bye, take care, good afternoon, and see you again.